All right, today we're going to talk about acceleration. Okay, we're talking about acceleration. This is a continuation of motion. Okay, acceleration is defined as the rate of change of velocity. Okay, so however much velocity changes or speed. Okay, we use velocity because it is a vector. Okay, because acceleration is also a vector like velocity. What does it mean for something to be a vector? No, sir. What does it mean for something to be a vector? Anybody? Levi, what's it mean for something to be a vector? Owen? That's not an answer. A vector means it has both a size and a direction, or as the fourth bullet says, a magnitude and a direction, okay? When we talked the other day, I want you to turn the left light switch off. When we talked the other day, whenever we were demonstrating motion, okay, distance and displacement, we had Owen walk forward, and he had a positive, thank you, sir. He had a positive displacement. When he walked backwards, he had a negative displacement. Recall that now? Okay, that's both our size and our direction. Okay. When velocity changes, so does the acceleration. Okay, so does the acceleration. When have you noticed something like acceleration really changing? I mean, when a car turns, acceleration changes. But have you ever been in the car, somebody drives really fast, like Stephen Willis, and he sits there and he gets in the car, he hammers the gas pedal down. And then when he stop, what's he do? Does he kind of let off and then let the car coast, or does he go directly from the gas to brake? If you got somebody who's going directly from the gas to brake and they're stopping really fast, yeah, that's a negative acceleration. Okay, that's still what we want to talk about there. So we've all seen, I have two trucks. I have a Ford diesel truck and I have a Chevy truck, gas truck. Which one's going to have the faster acceleration? Which one can I make go? Which one can go faster, quicker? The one with gas has faster acceleration. Okay, that diesel kind of takes a long time, kind of get it all going. Okay, the gas has more compression in it, so it accelerates very quickly. Acceleration is always length divided by time squared. Okay, the units in here we'll use most of the time is meters per second squared. Okay, meters per second squared, and then our equation, our average acceleration, as what we have is the rate of change of velocity over time. So change of velocity over change in time. Symbolically, I like that acceleration equals VF minus VI divided by TF minus TI. Okay. So we're going to use that equation towards the end of the day today. Let me find my mouse so I can click. So acceleration is the rate of change of velocity. Okay, average acceleration. Okay, there's our equation again. Okay. There's our equation again. So from this, okay, from this graph, we can see, okay, there's two equations here that we really want to talk about. Let me back this up. Today will only be let me find my mouse. Today will only be this top equation, the average acceleration, but I can find the final velocity. These two equations are the same thing, okay? These two equations are the same thing. They're just solved for different things. This one's solved for acceleration. This one is solved for final velocity, okay? But in here, we have, here's a graph of somebody's acceleration. Here's our 2 points, okay? And this line is showing the acceleration, okay? This line is showing the acceleration. This line, the blue line, is showing the average acceleration, okay? The final velocity minus the initial velocity divided by final time minus initial time. Sometimes you'll see a thing, negative acceleration, called deceleration, okay? That is, it's kind of correct, okay? I'll probably refer to that term a lot, okay? But, when the sign of the velocity and acceleration are the same, then speed is increasing, okay? Now, if the sign of the velocity and acceleration are opposite, then speed is decreasing, okay? So you can have a negative acceleration, but a positive velocity, okay? A negative acceleration, but a positive velocity. So when you're slowing down in your car, your velocity is decreasing, isn't it? You're going from, say, 50 mile an hour to 30 mile an hour. Your speed is decreasing. Your velocity is decreasing. But your acceleration, your acceleration is still increasing, okay? But it's just negative in there, okay? Now I went over this. Average acceleration is the slope of the line connecting the two. Oh, no, we were plotting velocity versus time. So a distance time graph is speed. A displacement time graph is velocity. A velocity time graph is acceleration. All right, instantaneous and uniform acceleration, okay? If the acceleration is uniform, the average acceleration will be equal to the instantaneous acceleration. How do we find, do we have anything in our car that shows the instantaneous acceleration? No. Stop the speedometer. Speedometer shows the instantaneous speed, not the instantaneous acceleration, okay? There's nothing in there that shows the instantaneous acceleration. But we've all heard that, you've all heard the ads of the car that's saying the car can go from 0 to 60 seconds in 2.7 seconds. You've all seen those commercials? Okay, that's acceleration. There's nothing in your car that shows you acceleration. There's no law against acceleration. You can go as fast as you want to go, as quickly as you want to go. Okay, you can speed up as quickly as you want. But you can speed up as quickly as you want, but there's a speed limit to get into there. So there's nothing in your car that actually shows instantaneous acceleration. I cannot find my mouse anymore. Okay, so we're going to look at this graph in 3 different ways. Okay, this graph, I've got 3 slides of this. I've got this graph showing 3 times. The 3 points of the graph are, you can see the first part right here. Okay, see how it's kind of a different slope? You'll see that? Here's the second part of the graph from this point to this point. And then from this point to the end is the third part. And these are the same graphs, okay? These are the same graphs. They're just, the graphs are the same object, but they are just showing 3 different things, okay? So this one, the top graph is showing your position versus time. So that's your speed or velocity graph, okay? Your top one is. The second one is the velocity time, so that's your acceleration graph, okay? And then this third one is also showing your acceleration. So for the first stage, from point 0 to like point B, I don't know, it's kind of hard to see in there, okay? From A to B, this is the first part we're talking about, okay? Velocity and acceleration, they are both increasing, aren't they? Are they both increasing from A to B and from A to B? Is that increasing? Is the slope positive or negative? Positive, so that means it is increasing. So in that case, you could say the car is speeding up, okay? From A to B, the car is speeding up. So the speeding up. The velocity is increasing. The red arrows are getting longer in there, okay? But is the acceleration uniform? Is it a straight line? Is the acceleration uniform? Is that a straight line? Remember, we're talking about acceleration. We should be looking at the velocity time graph. That's a straight line, isn't it? There's no curve in it like you see. Like this part has a little curve in it, doesn't it? But in that one, it is positive, okay? So that's the first stage. So you can say in the first stage, it is speeding up. Okay, the second stage, so this is from point B to point C. Point B to point C, okay? You're not speeding up, are you? Is the slope of the position time graph changing? Or is it a straight line? It's a straight line, so that means the velocity is not changing, okay? It's changing, but it's going up at the same rate, okay? It's uniform velocity, so we're not changing, okay? So, and that's why you see, is he accelerating right here? No. So like when I want to say that's your car's on cruise control, okay? So if you put your vehicle on cruise control, you have no acceleration, okay? So we decided in the first stage, he sped up. Now he's going into constant speed, he's on cruise control, okay? And then the last stage, what's happening? He's slowing down. The velocity is putting from a steeper line to a flatter line. And you'll notice that's here, okay? That is here. Did he stop? Yes or no? Did he come to a complete stop in this graph? Owen says no. Levi Wildarius, did he stop? Did the person stop? Yes. You won't always necessarily stop, would you? But in this case, he did. Why? Because is this a flat line? Is his position changing at the end of it? No. So that's how you know he stopped, okay? You can't look at this to see if he stopped because he could have sped up, cruise control, sped up, cruise control, okay? So that is acceleration. That's a 3-stage. I will love to, you'll have homework questions about these, okay? We'll have homework questions about these. Not today, but we'll have a graph day about it. All right, so our last thing we're talking about today is we're actually going to work some examples, okay? So I would probably advise you to write these down or, we'll work them out. My handwriting is not always going to be the greatest. My handwriting is not going to be the greatest. So it tells you a woman traveling by car has a constant velocity of 5 meters per second. When she steps on the gas and makes the car accelerate forward. Further, past 10 seconds, she stops the acceleration and continues at a constant velocity of 25 meters per second. Calculate the acceleration of the car. So, make sure I got the correct screen shared. All right, so I know this is kind of a bad thing in this, but what was my, I had 3 numbers in there, didn't I? What was our initial velocity? What was the person's initial velocity? What was our initial velocity? You're not even looking. What was our initial velocity? Do I need to play the crickets sound again? What was our initial velocity? 5. Okay, so back on this side over here, I'm going to write on my paint, I'm going to write VI equals 5 meters per second. Let me erase that 5 because that looks really bad. Equals 5 meters per second. Okay. Do I have another velocity? Her final velocity, what was it? 25. Okay, what about her time? How long did this take? $10 seconds. Okay. So T equals 10 seconds. So my acceleration equals VF, this was an equation I had from earlier spots, minus VI over T. So now I'm just going to plug my numbers in. 25 minus 5 over 10. So someone tell me the answer. What? What's the answer? What's 20 over 10? 25 minus 5 divided by 10. So what's the answer? 20 over 10. What's that equal out to? What's 20 divided by 10? 20 divided by 10? 2. So our acceleration equals 2 meters per second squared. Okay? Let's do another one. So Example two. Let me find my mouse again. There we go. Example two, a race car accelerates from 15 meters per second to 35 meters per second in 3 seconds. What is its average acceleration? Oop. So, not bad. Do that again. Find my mouse. I'll just put that, copy and paste that on the paint. That didn't work out. Undo. Let's do it this way. Okay, so there's my question. Okay, race car accelerates from 15 meters per second to 35 meters per second in 3 seconds. What is its average acceleration? So, when I'm talking about acceleration, I'm looking for 3 things: VF, VI, and T. So we're always going to write those 3 things down. Okay. So we'll go through. Each person tells you one thing. So you tell me something you know, and you tell me, is it VF, VI, or T? 3 people, 3 pieces of information. My bad. T is what? Okay, what's the value of T in this problem? 3 seconds. So Wildarius told me time was 3 seconds. Thank you, Wildarius. So you two have 2 other things to tell me. Not Wildarius. VF or VI? VI, okay, is what? No. VF is the final velocity, okay? What did you say that again? Did you say VF was what? VI is what? 15. VI is 15. That's what it starts out at. So 15 meters per second. And finally, that leaves you. Levi, what is VF? What's the final velocity? 35. Now, VF will not always be bigger than VI, okay? So now I'm going to plug this in my equation. A equals VF, which is 35, minus VI, divided by time. So someone tell me the answer. So 20 over 3. So what's the answer? You have a calculator on your computer. Oops, I'm sorry. There's only one person putting it in the calculator. That'll make me fall asleep. Give me 3 numbers. It actually runs 6.67, but I would take 6.66. And what are my units, Owen? What are my units? Meters per second squared. Okay, one more example. A car moving at 80 miles an hour has a speed of 35.8 meters per second. What acceleration would it have if it took 5.0 seconds to come to a complete stop? So I've got my three things I'm looking for there again. VF, which is final velocity, VI, which is initial velocity, and time. So Ladarius gave me time this time, so he can't give me time. But somebody else give me something you know. We need to fill out those three variables. VF is what? What's the final velocity? No, sir. Read the question aloud, Ladarius. Meters per second, yes, sir. So what's its final velocity if it comes to a complete stop? 0. So VF in this case is 0. 0 meters per second. What's its initial velocity? Well, I don't want to use 80 miles an hour because we're in science where our final velocity is in meters per second. So instead of 80, what would you say? $35.8, yes. 35.8 is 80 miles an hour, okay? And what about the time? 5.0 seconds. So now, acceleration equals what acceleration equals? How would I plug this in there? How would I solve for this? I would tell you it's VF minus VI over T. Over 5. Like 7 points. What's the answer? Wrong. You're very close. It's not 7.16. It is negative 7.16, wouldn't it? Because it's negative. The car's stopping fast. Negative 7.16. Why is it negative? Because is the car stopping? Car's slowing down. Anytime if it's stopping, it's slowing down. So, any questions about anything? I know you people never ask questions. You don't talk. Okay.